This video is on section 4.1 notes, exponential functions and their applications. So first, I put in the notes this table of exponents and some of their values, just so that they would be at your fingertips, but then also to remind you what happens if you have a negative exponent. So a lot of these should be familiar, especially, 2 to an exponent, 4 to an exponent, 5, maybe 3. But specifically, a lot of students forget that if you raise a number to the 0 power, you always get 1. So we have a lot of kind of repetitive values here. And that if you raise a number to a negative exponent, it actually turns that number into a fraction. So 2 to the negative 1 is the same as 1 over 2 to the positive 1, or 1/2. 2 to the negative 2 is the same as 1 over 2 to the positive 2, or 1/4. 2 to the negative 3 is the same as 1 over 2 to the positive third, or 1/8. And that's going to be important for this lesson for you to remember. Additionally, one thing I want you to notice is that if we are looking at exponents in this way, there is no way to take a number and raise it to any exponent and get 0 as the answer. You can get 1 as the answer when you raise it to the 0 power, and you can get fractions, and your fractions can get very, very small, but you can never plug a number into an exponent and end up getting 0 as an answer, and that is something that's important for exponential graphs. Okay, so this is here for you to refer to if you need it for any of the problems. All right, so first, the definition of an exponential function is that it is a function with a base, and they use a. I don't like to use a because we called that our stretch factor when we use transformations. So in the notes, I just wrote the word base. But here it says with a base a function of the form f of x or y equals a to the x, where x is any real number and a is a real constant, where a is a positive number and it's not 1. So it's just something other than 1 that's not negative. It's not saying that you can't have a negative in the front. You can. That would reflect the graph over the x-axis, which is something that we've seen before. So a function is an exponential growth function if the base is greater than 1. So if this a value, the base of the exponent, is greater than 1. And it's an exponential decay function if the base is in between 0 and 1. So if you see a base and it's a fraction, basically, then that means that the graph is going to decay. It's going to get smaller exponentially, like as time continues. And if the base is greater than 1, that means it's getting larger as time goes on. All right, so for example, we're going to evaluate some functions, but we're also going to say what their bases are and if they're growth or decay. So we have f of x is 4 to the x, and here they ask us to evaluate f of 3/2, but also to say what the base is and to say if the function is growth or decay. So f of x, 4 to the x, the base is 4. This would be exponential growth because 4 is greater than 1. From there, we can go ahead and actually do the evaluation. So we're going to say f of 3/2 is 4 to the 3/2. And you can do either part of the exponent first. If you recall, anytime you have a rational exponent like that, it means that you have a root of some sort. So you can take the 2 and do the square root of 4 and then raise it to the 3rd power, or you could do 4 raised to the 3rd power and get the result and then square root that. I like to do the root first. I like to make my numbers small before I make them larger again. So I would do the square root of 4 raised to the 3rd power. Square root of 4 is 2. 2 raised to the 3rd power is 8. For the next problem, it says g of 3, so we're going to look at function g. The base of function g is 5. This is exponential growth. And then I'll go ahead and evaluate it. So g of 3 is 5 to the 2 minus 3. 2 minus 3 is -1, so this is 5 to the -1. Anytime we have an exponent that's negative, it just means that I should rewrite this problem as a fraction. So this would be 1 over 5 to the +1 exponent, which is just 1/5. And then last we have h of x. So h of x says 1/3 raised to the exponent of x. So the base is 1/3. That means that this is an exponential decay function. And then to evaluate the expression, I'll say h of -2 is 1/3 to the -2. And if you recall your exponential rules, anytime you have a fraction raised to an exponent, you just have to remember to use that exponent on the numerator and the denominator. So this is 1 to the -2 over 3 to the -2. And then to take those exponents and make them positive, you just take them and move them to the opposite side of the fraction. So 1 to the -2 would be 1 to the +2 in the denominator. 3 to the -2 would be 3 to the +2 in the numerator. So 3 squared is 9, 1 squared is 1, and so this is just 9. All right, on the next page of the notes, we're going to be looking at the graphs of exponential functions. So these are somewhat similar. You can see that I did less points than I would often do for typical graphs. A lot of times I would do x values from -2 to +2, and I just did -1 here. But you could have done -2, and that would have given you 2 to the -2nd power, which is 1/4, and we certainly could have done that as well. What I added in here is that we have a horizontal asymptote of y equals 0. And this is what I was talking about in the very beginning of the video, that if we look at that table, there is no way for 2 to the x to have an output of 0. And there's no way for 2 to the x to have a negative output either. So there's a lot of values that are going to be restricted when we talk about our range for a graph like this. So I wrote that my horizontal asymptote is y equals 0, which is this horizontal line right here, the x-axis. And in this case, the curve gets really close to that asymptote, but it doesn't cross it. So over here, we're going to do 3 to the x. So I'll go ahead and use those same values. So 3 to the -1 power is 1/3. 3 to the 0 power is 1. 3 to the first is 3, and 3 to the second is 9. So I've got -1, 1/3, 0, 1, 1, 3, and then 2, 9 is too large for the graph that I have. And it looks like this. And you can always draw in that horizontal asymptote. We have the same horizontal asymptote this time. If you look at those values for 3, we can see that you're never going to get 0 exactly as an output, and you're also never going to get negative outputs. So I can write that that horizontal asymptote again is 0, and you could also draw it in if you wanted to. In fact, I would say go ahead and draw it in, because that's what I'm going to expect you to do on the graphs that have transformations. So it's good practice to do it here as well. So here's another parent function, 3 to the x instead of 2 to the x. You can see that they're very similar. This one is just going to grow a little bit faster. So the domain and range for each of the graphs, the domain is going to be all real numbers, -infinity to +infinity. There's no limitation to what x values you can plug into an equation. You can have any negative x values for the exponents. They're just going to give you fractions. You can have positive x values as exponents. They're just going to give you large numbers. You can plug 0 in. It doesn't matter what you plug in. You're always going to get an answer. The range, however, is limited because you're never going to get 0 as an answer, and you're never going to get a negative number as an answer. So the range is from 0 to infinity. All right, so here are some properties of an exponential function. The function is increasing if it's exponential growth. It's decreasing if it's exponential decay. We're always going to have a y-intercept for the graph. If it looks like this, if it's a parent function for that exponential graph, then it's always going to have a y-intercept of 0, 1. The graph is always going to have the x-axis, or the line y equals 0, as a horizontal asymptote as long as no transformations have happened. The domain and the range are always going to be the same as long as no transformations have happened. And the function is 1 to 1. And if you recall, 1 to 1, it just means that you can take the inverse of the function and get a function as the result. So here I went ahead and wrote down, this is the parent function, some sort of base to the x, 2 to the x, 3 to the x, 10 to the x, anything you can think of to the x power. And then here are the transformations. And the transformations are exactly what we have looked at before. So the number in front is going to reflect the graph over the x-axis if it's negative. If the number in the front is larger than 1, it's going to stretch the graph. It's going to make it look taller and thinner. If the number for the a value is a fraction that is less than 1, or a decimal that's less than 1, it's going to make the graph shrink or compress, and it's going to appear shorter and wider. The h value moves the graph to the left or to the right, and it's the opposite of what you would think. Plus a number moves it to the left, minus a number moves it to the right. And then the number on the end moves the graph up or down. So we're going to go ahead and use those transformations to take this parent function, y equals 2 to the x, and complete these transformations on this graph. So first, they kind of wrote it in a different order than I am comfortable with, so I'm going to rewrite it up here. I'm going to say 2 to the x plus 3 with a minus 4 on the end. The 2 is not a transformation, it's not a stretch, it is the base. So it's not the a value in the front, it is the base of the exponent. So that's not a transformation, that's the parent graph. But from there I can see that I have 2 transformations. This graph has shifted to the left 3 and down 4. So left 3 and down 4. So typically when I work with these graphs, I might be able to make this table for the parent function, but I really just focus on these 2 points right here. I always start with 0, 1, and then 1, and whatever the base of the exponent is. And that's important. This is the base. So if your graph has a base of 2, you're going to use 2. If you have 3 to the x, you're going to use 3. If you have 7 to the x, you're going to use 7. So whatever your base is right here. And then I always use the horizontal asymptote. We're always going to draw that in. So over here, I'm going to take these points. I'm going to shift the points left 3 and down 4. So left 3, left 3. The horizontal asymptote is a line that looks like this, and so if I shift it left 3, it's still in the same spot, so I'm not going to adjust that just yet. Next, I'm going to shift the points down 4. So 1 minus 4 is negative 3. 2 minus 4 is negative 2. And then the horizontal asymptote, if I shift it down 4, it's actually going to move. So instead of being y equals 0, it's going to be y equals negative 4. So here is the horizontal asymptote, and then left 3 down 3, and then left 2 down 2. And so our graph is going to look something like this. So the domain, left and right forever, any value can be plugged in as an exponent. For the range, the very lowest that this graph goes is negative 4, but it doesn't touch negative 4, it just gets close to negative 4, and it goes up forever. So negative 4 to infinity. All right, we're going to try another problem that's similar to that. So this one has E as the base, and you might have heard of E, you might not have heard of E. This is Euler's number. Euler's number. Don't say Euler, say Euler. And it's a button on your calculator. The reason it's pronounced that way is I think it's German, but it's not an English name or an American name, so that's why it's pronounced a little bit different than we would expect. So Euler's number, if you look right here in blue, you can see e to the x. It's typically raised to an exponent. So since it's in blue, I'm going to hit the second button. And I just want to know what e is all by itself, so I'm going to raise it to the first power. E to the first is 2.718. And you can think of it kind of like pi. It just is a number that represents a decimal, and it's one that we kind of memorize. Okay, so just like the page before, we know that we have the 0.01. Plug in 0 for the exponent, you get 1 as an output. Plug in 1 for the exponent, you get e to the 1, which is e. Or if you want to write 2.718, you can. And then we have the horizontal asymptote y equals 0. Now, when you do transformations, you don't have to do the parent function to begin with. You could just go straight to doing the transformations if you're okay with writing this and not drawing it. But I'm going to go ahead and draw it since these are our notes. So over 1 up 2.7. So something like that. There's the horizontal asymptote. Okay, so there's our exponential function. So now we're going to take this exponential function. It has the same base. This is the parent function. So the e is not a transformation. The transformations are that negative in the front. So we are going to reflect it over the x-axis. Right one. And up 2. Okay, so to reflect it over the x-axis, I'm going to take my y-coordinates and I'm going to multiply them by a negative or multiply them by -1. So my x's are going to stay the same and my y's are going to be -1. And I'm just going to write down here that this is that decimal 2.718. So this is -2.718. Okay, and then I'm going to shift the points right 1. So I'm going to take the x-coordinates and add 1. And then shift the y-coordinates up 2. So I'm going to add 2 and add 2. -0.718. Okay, the horizontal asymptote, when I shifted it to the right 1, it didn't move anywhere. But when I shifted it up 2, it moved. So horizontal asymptote y equals 2. Okay, so I can go ahead and draw this in. So we've got 1, 1, and we've got 2, -0.7. And so this is what the graph looks like. And I always know how to draw the graph. The easiest way if you're struggling is to start with the point that's furthest away from the asymptote and then draw it to the next point and then follow the asymptote. So either follow it towards the left or follow it towards the right, whichever one makes sense with the points that you have. But start furthest away and then you know that the curve has to follow the asymptote. All right, so that's how to graph exponential equations or exponential functions. Now we want to look at how to solve exponential equations, and we're going to do that by changing the base. You might not have all these numbers memorized in your head. That's fine. You do have that chart on the first page of the notes, which is why I gave it to you. So to solve this exponential equation, it's going to be beneficial for us to make sure that we have the same base for both exponential expressions, the one on the left and the one on the right. So if I had like 3 to the k equals 3 to the second, well then I'd be like, well, k equals 2, that's easy. So if we have something like this where the bases are not the same, the easiest way to do the problem is going to be to take diagram right here that has all of our exponential functions and their numbers, their outputs, and figure out a way to rewrite them so the base is the same. So for the first problem, we have 125 and 5. So if I look and find what column has 125 and 5 in the same column, it would be the 5's column. So here's where I have 125 and 5 in the same column. So the 5 is already written. These are the bases of 5, and I add 5 to the second. So that one's already written as a base of 5. The 125, however, is not written as a base of 5. So I'm going to rewrite it. I'm going to take it and write it as 5 to the third. So that's 5 to the second already. I'm going to take the left side and write this as 5 to the third. And then the 125 was raised to the 3k, so I'm going to take this 5 to the third and I'm going to raise it to the 3k. And from here, I just have to remember my exponential rules. What happens when I take an exponent and raise it to an exponent. And if you recall, an exponent raised to an exponent, to do that math, you just have to multiply the exponents out. So 3 times 3k is 9k. And then this is where you get to the point where it looks like the one-to-one property of exponential functions. At this stage, you can say, well, if the bases are the same, the exponents should be the same as well. So 9k needs to equal 2. And then I can go ahead and just divide by 9. K equals 2/9. And it's pretty easy to go back and check my work. I would just take 2/9 and save that as x. I always use x. You could use k if you wanted. And I'm going to make sure that 125 to the 3x is the same as 5 squared. And 5 squared is 25. So I know I got that answer right. Okay, let's try this again. So I'm going to look to see where 64 and 16, sorry, 1/64 and 16 are in the same column. So 1/64 and 16, there's 16, there's 1/64, so I can do the 4s. And if you were thinking along with me and you were thinking, oh, but what about the 2s? You can also use the 2s. 1/64 would have been 2 to the negative 6. So 2 to the negative 6 would give you 1/64, and then 2 to the 4th gives you 16. So this particular problem, you can use a base of 4 or a base of 2. You're going to get the same answer. I'm going to go ahead and use a base of 4. So we had 1/64, and we had 16. So the 1/64 is going to change to 4 to the negative 3rd, and the 16 is going to change to 4 to the 2nd. So I have 4 to the 2nd, which is raised to the 2x minus 2. 1/64 is going to be 4 to the negative 3rd power. And again, I have to remember my exponential rules. So I have an exponent raised to an exponent. So that means I'm going to multiply those two exponents together. 2 multiplied by 2x minus 2. I'm going to think of it like this. 2 multiplied by 2x minus 2. That means I have to distribute the 2, and I'm going to get an exponent of 4x minus 4. And then at this point I can say, all right, if the bases are the same, the exponents must be the same as well. And then I can go ahead and solve that equation. So 4x equals 1. And then I'll divide by 4. And so x is 1/4. And you can plug this into your calculator as well and make sure that your answer is right. All right, for the application problems, we have multiple formulas for compound interest. So the first one is just the regular compound interest formula. It says if a principal P, so some starting amount or initial value, is invested for T years at an annual rate R, and I want you to write next to R that this is the decimal form. So they always give you the rate as a percentage, and then you have to take that percentage and write it as a decimal, convert it into the decimal form. Compounded n times per year, then the amount A or the ending balance is given by this formula. So compounded n times per year, we're going to write down some of the common compounding intervals, I guess you could say. So for n, they might say annually. If it's annually, that just means 1. If they say monthly, that means 12. If they say weekly, that means 52 weeks in a year. If they say daily, that would be 365 because there's 365 days in a year. So there are other options. They might say like quarterly, that would be 4 times a year. There's 4 quarters in a year. Semi-annually would be twice a year. So there's other options, but here's some samples for you. Okay, so for this example, it says find the amount or the future value in an account when a principal of $20,000 is invested at 6% interest compounded daily for 3 years. So 6% interest means that R is 0.06. So whenever you have a percentage and you need to write it as a decimal, you just take the whole number, the 6 and 6%. And the whole number would have a decimal right here, and you just move it 2 places to the left. So 0.06 is the rate. Compounded daily means that n is 365. For 3 years means that the t value is 3. Principal of 20,000 means that p is 20,000. So we have all of the values. We're just going to go ahead and plug them into that formula. So the final amount is going to be 20,000 times 1 plus 0.06 divided by 365 to an exponent of 365 times 3. And we'll see what that is. I wrote a squiggly equal sign because I know I'm going to probably have to round the number when I write it, but you can write a regular equal sign. It doesn't matter. So here's what I'm typing in. I've got the 20,000 and then 1 plus 0.06 divided by 365. 365 times 3. You can plug in the 0.06 divided by 365 as a fraction. It doesn't matter. You'll get the same answer either way. So this is $23,943.99 that would be the future value of the account in 3 years. Okay, so that is the compound interest formula. We also have another formula that is for continuous compounding. So it says if a principal P is invested for T years at an annual rate R compounded continuously, then the ending balance is PE to the RT, and we're going to be using Euler's number, that E value 2.718, that button on our calculator to calculate this. So it says find the amount or future value when a principal of $5,600 is invested at a 6.25 annual rate. So 0.0625. So I just am taking the decimal place for the percentage and I'm moving it 2 places to the left. 0.0625 is the R value. Compounded continuously, this wording doesn't tell us to plug a number in. It tells us to use the formula PE to the RT. For 5 years and 9 months. So time is the number of years, 5 years and 9 months. If we're going to convert 9 months into years, I'm going to say 5 years plus 9 months out of 12 months. So 5 years plus 9 months out of 12 months is 5.75 years. So 5.75 years. Right, so I'm going to say the final amount is the principal times e to the 0.0625 times 5.75. Remember, the E button is right down here in blue. So 0.0625 times 5.75. We get $8,021.63. All right, so this one, I put the answer here because I didn't want you to have to do all the calculations, but I'm going to read the instructions so you can see what's happening. So it says find the future value of an account when a principal of $10,000 is invested with 12% interest compounded annually, quarterly, monthly, daily, hourly, and continuously for 1 year. So when it says compounded and it has all these are telling you to use A equals P 1 plus R over N to the NT. All those words are telling you to use the first formula. Then when it says and continuously, that one is telling you to use not Y equals. This one is telling you to use A equals PE to the RT. So if you see the word continuously, you use this formula. If you see some other value that you can plug in for that N, you use this formula. And what they're doing is they're showing you the final amounts based on how often you're getting interest on the money. So if you're getting interest which is compounded annually, that means that once a year they're going to look at how much money you have in the account and they're going to calculate the interest and they're going to give you the interest for your account. Quarterly means that 4 quarters in a year, that's every 3 months. Every 3 months, they would look at how much money you have in the account and they would give you your interest. Monthly means that every month, 12 times a year, they would look at how much money you have in your account, they would give you interest. Daily, every single day, they're looking at how much money you have in your account, they're giving you interest. Hourly, every single hour, they're looking at how much money is in your account and they're giving you the interest based on that money. And then continuously is hard to conceptualize, but it just means that they are constantly looking at how much money is in your account and they're giving you interest for that. So if you look at this, you can see that really you want to be compounding interest continuously. That's what's going to give you the greatest amount of money in your account over time. But you can see that the difference between getting interest hourly and the difference between getting interest continuously, those are just about the same, a penny difference. So you'll see there's not a significant difference there, but there is a big difference between getting the interest once per year and getting it continuously or getting it hourly. You can see $74 or about $75 difference there. So this is just so you can really see what changes depending on how often that interest is compounded. And then you can see here, it just said for 1 year, but you can see the way that the numbers are plugged in. So there's your 12%, and then annually, so just 1 and 1. Quarterly, there's the 4 and the 4. Monthly, the 12 and the 12, 365. The exponents were not multiplied by anything because it was just for 1 year.